All right, well, participants are popping in. It's always fun to watch that ticker down below. We're at over 40 now. I just want to welcome you to the second half, part 2 of Seamless AI Sessions, or Seamless AI Systems, thank you. And hopefully you had a chance to join us earlier, and if you didn't, we have that wonderful Slack channel so you can see what the conversation looked like earlier today. I believe you're seeing my screen. So we have 4 excellent talks, probably quite a bit of time for Q&A, I hope. And basically the rundown is going to be, let me go to the notes here really quickly. We have, please plan to speak for 12 minutes, leaving 2 minutes for questions for the regular talks. And for the highlighted talk, please speak for 15 minutes and try to reserve 5 minutes for questions. And we'll be agile there. Yes, and we have, right, Mayank is the first speaker. And so without any further delay, why don't you go ahead and show your slides. And Brian Meyer, thank you so much. And Lindsay are helping us keep this session running smooth. Brian's going to give you a 2-minute warning. And also the only place to have our discussion is in Slack. So if you look in the chat, you'll see a nice link to Slack. And Mayank, Kejriwal, thank you so much for joining us today. Please take it away.
All right, thank you. Thank you everyone for coming. Can everyone hear me and see my slides?
Yes, looks wonderful. Thank you.
All right, thanks. All right, so I want to start by saying that this is a very new community for me. I actually don't know a lot about oceanic or environmental sciences, and that ironically is where the challenge and the opportunity for the technology that I'm going to talk about today lies. And that's a knowledge graph. So I want to tell you a little bit about these things called domain-specific knowledge graphs that we have applied in many domains, and we are hoping to apply it for enabling applications in this domain as well. And looking forward to getting to know many of you and hopefully collaborate on this in the future. Okay, so just a little bit about me. So I'm a professor in the University of Southern California's School of Engineering. And my area of expertise is in applied AI. So I build AI technologies that are then applied in collaboration with domain experts. So just some examples are people in industry with e-commerce. This is like Amazon, Verizon, and so on. I've done a lot of work in human trafficking, and then also crisis response, where we use social media and other data sets to build domain-specific crisis response systems. So in many of these projects, we use a technology that is called a knowledge graph. Now, what is a knowledge graph? For those of you who have not seen it before, I want to provide a couple of formal definitions, but there's also a very intuitive visualization on the left-hand side. And it's basically a graph. So you have nodes and edges, and the edges are directed, and everything has labels on it. And a set theoretic definition is that it's a set of triples of the form head entity, relation, tail entity. So these are like your edges over here, where you have Bob Dylan, lives in, hold on. Bob Dylan, excuse me, Bob Dylan has gender male, Bob Dylan lives in the United States, and so on. And so these are triples, right? They are tuples with 3 elements, and this is the set theoretic definition. There's a graph theoretic definition, which is more intuitive, which is that it's a multi-relational directed labeled graph where the labels have semantics. And this is very important, the fact that the labels have semantics, because it means that not every graph is a knowledge graph. So there has to be some notion of semantics, and these could be encyclopedic, such as from Wikipedia. They could be common sense semantics, but what we are really interested in is domain-specific semantics. So semantics that come from a domain, and we'll see how we can arrive at such semantics. But before I go a little bit into the domain-specific KGs, I do want to actually point out that most likely you have seen a knowledge graph before, especially of the encyclopedic kind. And so if you think about Google, when you search for something like places to visit San Jose in Google, once upon a time, about 10 to 12 years ago, if you search for something like this, you would only see a list of web pages. you would not see all this other stuff that you're now seeing over here, where Google is actually able to understand that San Jose is a place, and that places to visit are tourist locations in San Jose, and it shows you what we call a knowledge panel about San Jose. It shows you recommendations, related to San Jose, like travel recommendations, exploration suggestions to explore other places, and so on. And so, where is all this coming from? Because this is very general, right? If you replace San Jose with Los Angeles, with Washington D.C., if you um, replace it with things like movies to see right now, and so on, you'll see something very similar. You'll see similar elements pop up in the search engine. And so this is coming from the Google knowledge graph. So the underlying technology that results in this, in all these things that you see, surrounding the list of web pages, is coming from the Google knowledge graph. Now, why KGs and not databases or text? And the reason is that it straddles the sweet spot between databases, which are very structured. They have very strong semantics and logic and structure. But the problem is that they are not very human readable, right? And we're all, any of us who have dealt with databases know that, where it's very difficult to actually interpret this, like what's going on over here. And the other side is text, right, which is very human readable, but machines are still not very good at actually reading text, despite all the advances in NLP. And so KGs are a very sweet spot where they're kind of human readable, but at the same time, they also have a lot of structure. And so they enable the kinds of applications like you saw with the Google Knowledge Graph. And there are many applications for KGs. So, I've listed these in order of relevance to the scientific community. And some of this is, scientific text mining. So if you have lots and lots of papers, and you want to build a knowledge graph over the corpus of papers in your field, then it allows you to search for, to sort of build a search engine over the papers. There's question answering. There's a lot of technology, a lot of advances on that, especially using language models like GPT-3 and, other models that you may have heard about. As we go down, it sort of starts getting more into e-commerce and media, but they are still very important, I think, in the scientific domain as well, especially summarization, where you want to summarize an entire paper into a sets of entities and relations that then get into a knowledge graph. So how do we construct a domain-specific knowledge graph? So this is a complete pipeline. We won't have time to go into all of it because it's each of these is a separate field of research in its own right. But I do want to sort of walk you through the very high-level workflow. So the first step is to gather the data, which is the corpus, whether that's scientific papers, it could be multimodal data like images, it could be databases, it could be a mixture of all of these. So there's a corpus over which we want to build a knowledge graph. And then there's the ontology or the domain model from which your domain from which your domain semantics are coming. By the way, the things that you see in the gray boxes are the fields of research in AI and computer science that tend to do a lot of research on these different sub areas. So it's very interdisciplinary, and it's in order to build a full seamless application, we have to really combine these end to end in a full infrastructure. Once you have the corpus, you have to construct an initial KG using NLP techniques, usually, like information extraction and so on. A lot of deep learning comes in this part of the pipeline. The initial KG is usually very rough. There might be duplicated entities. There might be edges that are incorrect. There may be missing edges. So then we have to do what's called KG identification, where we solve some of these problems and have a more complete and refined KG. And then that goes into an infrastructure, and then that is used to access the end user, or is used to provide access to end user tasks and applications. So just in the last few minutes that I have remaining, I just want to go a little bit into domain ontology, because I think this is very important. It's the primary point of intersection between the subject matter experts. So these are the scientists, the e-commerce experts, the social scientists, whatever the domain is over which we're building this, and the computer science and AI experts. That would be people like me who researching the technologies to build these things. And in different fields, you have different ontologies. So in biology, the gene ontology is very famous. In chemistry, the PubChem and Chevy ontology are very well known. In social networks, we have friend of a friend. And I did some research in environmental and oceanic sciences, and I found that there are some ontologies. There are two that I found, but there are probably others as well. But one very good example is SWEET, right, which came from the NASA jet propulsion, and there are different terms and sub ontologies inside these boxes, and a lot of it is available in this doc file that I linked over here. But this is the kind of ontology that we want to use to build a knowledge graph from the corpus, I think, in this field. I want to just close out by showing you what it could look like, because we don't yet have a complete seamless application for the oceanic and atmospheric community, but we do have them for some other communities that we have built in our group. And so one of these is the crisis response, where, as you can see, this is the corpus, right? So you have the social media, news, broadcasts, and other things. This is our corpus. The language technology development environment comes from NLP. So this is the knowledge graph construction. We use this to extract data from the raw data. We put it into an initial KG, and then we apply analysis tools. And what comes out are these interfaces that are interactive and that can be used to develop a lot of different applications, things like terrain analysis, hotspot detection. So these are very domain specific. Depending on the domain, you will have different applications. And just in my last one or two slides, there's a lot of ongoing research and development, much of it collaborative. The reason that I wanted to come to this community is because I really do believe that there's an opportunity for us to build something like what I just showed for crisis response in this domain. And I really hope to get to know many of you, to start working on this problem, because I think it can facilitate many rich applications if we can build a knowledge graph in this domain. So in these 2 or 3 slides, I provided a lot of resources for those of you who might be interested in learning more about this. These are tutorials and survey papers. We wrote papers on how to apply this to COVID-19. Others have done that as well, so it's not just my work. And there are also books that we've written on this, and so there's a lot of work that has happened to make the field very mature. And the sort of last mile, in a way, is applying it to many different domains to make it to build these applications in a domain specific way. And we need to work with domain experts to do that, and to do something like what you saw with the Google knowledge graph. So that's our vision, that we can build that for many different domains in a very easy and seamless way, and make it very easy for you to work with lots of information.
1 minute.
Yeah, I'm done. Yeah.
It was fascinating. All right, I'm looking over at the Slack, and you've got a question from Nico. And he asks, what is the difference between an ontology and a knowledge graph?
That's a great question. So an ontology describes the concepts and properties. So for example, if we look at crisis response, then the ontology might contain the different kinds of events, like the earthquake and water contamination, food depletion, and so on, all those things. But the actual event, like let's say in Haiti, you have an actual earthquake, so that the instance, the actual event, the instance of the concept will be in the knowledge graph, but the concept itself will be in the ontology. So the ontology contains the concepts and properties, and the knowledge graph contains the instances that are extracted from the corpus.
Thank you so much. So feel free to join the Slack conversation if you want to share more there. And we'll go to the second speaker, which I may have misspoken on the order earlier, so thanks for figuring that out. This is Vidya Samadi, and the title is A Tour of End-to-End Deep Learning for Flood Image Classification and Floodwater Level Estimation. Are we there yet? So Vidya, please take it away. So we see your slide, but I think we don't hear you yet.
Oops. Can you hear me? Sorry.
Yes, I can.
I was muted.
Oh,
yes,
it happened.
yes. I'm Vidya Samadi from Clemson University, and I'm presenting part of our 2 NSF grant that we recently got awarded. So the title of my talk, as Rob mentioned, is about end-to-end deep learning methods for flood image classification and flood water level estimation. And I raise a question, are we there yet? And at the end of my presentation, I would answer to this question. So before I start, my computer is stuck. I want to give it, I'm sorry, an introduction about my research lab. We are Hydrosystem and Hydroinformatic Research Team, or HHR team at Clemson University, and our focus is on the interface of computer science and water resources engineering, and we develop computational modeling to deal with the water resources issues, but our focus is mostly on flood simulation and forecasting. So we are living in an exciting time, and there are many AI modeling systems that we can use actually in applied research. And it sometimes amazes me how other engineering fields can use other AI fields in, for instance, computer vision techniques in different fields in engineering, like self-driving cars, manufacturing and production lines, and how we could potentially use these techniques for crisis response, and particularly for flood-related research. But when we look at these techniques, we need data. And currently, when we work, we want to use this technique in flood-related research. We have a lack of flood images to train the models. And another issue that we have with using this technique is pre-processing of the images that is very time consuming, but it's very important to mitigate the effect of poor lighting and other alignment in order to use images. So motivation of our research was related to the successive hurricane event that we get in Southeast region. I'm sorry, I got stuck again. So
you want to?
yeah,
are you good? It's okay.
I need to stop and then reshare it again. Just yeah.
Okay.
Our motivation doing this research was about the successive hurricanes event, and also we call it a major that caused major flooding in our areas, particularly in South and Southeast region. And we, in addition to this mighty storm, we also get localized flooding in the Carolinas that impact our infrastructure system, impact our building, our community, our economy. So we actually started looking at these storms and working on the data that we had in order to better understand this extreme event. And then we look at the data, we found that about 80% of our data, they are in either videos or images, and they are unstructured data that could potentially use in flood-related research. And most of our citizens, they acting as a human sensor. Wherever they go, when we get floods, they capture the flood and then they put it in the social media, they share it. And also we have USGS river cameras that provide phenomenal information and images for us in order to use in our modeling system. We have Department of Transportation cameras that provide data. Some of them, they don't store it, unfortunately, but we do have those real-time information in order to use it in our modeling system. As I said, we have about 80% of our data are big data or image-based data that could potentially help us in order to make smart decision, particularly in near real time. So, but the key is here is we organize the data, whether we deal with the image data or with time series data. When we want to feed it in any modeling system, we got to organize them and enhance them and pre-process them in order to be to provide meaningful information for our modeling system. Both image-based data and as well as time series data, pre-processing of the data, filling the gap, or formatting the data, very important in order to provide meaningful information for any modeling system. So what we done here in order to develop a system to use big data as well as data analytics system was the developing flood analytic information system, or phase. We started sometime in 2018 to start this platform. And this platform actually got a lot of functions. If you visit floodanalytic.clemson.edu, you can see how we developed this smart application. It gathered all the information on data using API from different federal agency and different platforms. It got Twitter search and Twitter streaming API that gather the tweeters using and then links them and analyze them using NLP and intersect those tweets with watershed boundary as well as USGS flood gauging data in order to identify at least location. It also provides flood frequency analysis as well. Is very useful for professional engineers, and all you got to do is to provide USGS gauge ID and then analyze your flood peak rates and get a PDF report of your flood frequency analysis. But in this presentation, I'm going to focus only on data analytics. And I refer you and I encourage you to read our paper that is published in 2020, Environmental Modeling and Software. In order to develop data analytics system, we developed first a package. We call it Flood Image Classifier. It's a Python package. It got several algorithms in it, and we integrated in the phase application. But before we start, talking about this package, I want to talk about flood data set. We have a lack of flood images in order to train or deep learning modeling system and use those around 80% of image data in our flood related research. This is the workflow of this package. I want to briefly just take you through this process. We gather data from different platform, from USGS, from Twitters, from Department of Transportation. And we gathered those data that they had geolocation information, latitude and longitude, because we wanted to know where the flood occurs in order to compare or analyze with the USGS flood rating curve. And we gathered those information, we pre-process it, we train our data. And then after training, we provided labels, around 8 labels in order for our model to detect it, which I explain in the next slide. And then eventually the pipeline will we predict the labels and provide the inundation area and flood depth. So this is a workflow of flood image classifier. We currently have 5 algorithms in this package. We are adding other algorithms as well, and mostly they are CNN algorithm and other algorithms like deep neural network algorithm as well. And each algorithm is different than other one, and all of them were trained using more than 6,000 flood database that we created in this research and deployed at the IBM cloud service. So we train our data using various CNN algorithm and other deep neural network methods. We consider, as I said, 8 labels in order to train this algorithm. And then the things that we realize here is the best way to get the information from images is to label and detect those labels in the images and eliminate them. and then focus on the flood labels. So because flood label is very difficult to detect in the images. So what we done is, as I said, we consider 8 different labels, such as vehicle, forest, vegetation, critical infrastructure, and then we train the model to predict those labels. We eliminate these labels from the images, and then we eliminate it, and then we use the flood labels in order to understand the flood inundation area and the depth. So an interesting thing is we found that most of our models, they have difficulties in labeling and detecting vegetation, and they are doing very good job with critical infrastructure detection. So after we eliminated those 8 labels in the images, we had only flood in the images, and we used canny edge detection and aspect ratio concept in order to estimate the floodwater level as well as inundation area. And then we consider 11 labels, and based on aspect ratio, we classify them into low, moderate, and severe depth, as well as flood severity. So here you can see the same image that we trained the algorithm in order to eliminate other labels and just keep the flooded areas. And you can see here the model gives us level 3, which is low flood severity or risk classification, as well as the model calculated the area based on the dimension of the pixel. So here you can see briefly how our tools work. We just now integrated 3 algorithms. We are continuing training and then including more algorithm here in the data analytic part of the phase applications. So those algorithms are pre-trained. All got to do is just drag and drop your images here. It provides the labels as well as the area, the inundation area, and the depth based on the level that we predefine in the algorithm. Some take-home message. Yes. We found that accurately detecting various category or labels in the images are very, very important in order to provide predict the labels and provide accurate information to user. We found mask or CNN among all those CNN and deep neural network is the best model for both label detection, floodwater, excuse me, classification, and inundation area calculation. Our research shows promising results toward application of image-based system for flood monitoring that can easily embedded with the USGS river cameras in order to provide flood assessment in near real time. So addressing my question that I raised in my title, we found CNNs are doing amazing job with the images, but these models, they struggle with the small objects. If you have several flooded area in an image, it's a struggle to detect those images, and it needs many images to train, and it is very time consuming. But they are smart, and they are smart enough in order to detect severe flooding, which is our major issue when our road gets flooded, particularly in the Carolina. We have a lot of road flooding issues when we get the hurricanes here. And I want to acknowledge my students who helps me with the development of this package as well as a phase application. And I want to acknowledge NSF as well. So if you have any question, I would be happy to answer it if you have time. Thank you.
Well, this is a fascinating talk. Thank you so much. I don't see any popping up just yet. In spirit of time, we'll go to the next speaker. But Vidya, it was a wonderful talk. Please check the Slack channel for questions from our audience. All right, Enrico. So please feel free to share your screen, and it looks like you're good to go.
Presentation. Okay, well, hello everybody. My name is Enrico Camporeale. I work with CU Boulder and NOAA Space Weather Prediction Center. So first of all, let me thank you for this opportunity to present this work. This is about a new method called ACCRUE, which stands for Accurate and Reliable Uncertainty Estimate. And basically, it's a method that takes your favorite deterministic model and transforms it into a probabilistic model, meaning that it associates sort of an optimal error bar on top of your deterministic model. So I guess everybody is familiar with what the deterministic model means, but nevertheless, let me spend a minute to explain. So deterministic model basically it's a model that takes a set of inputs, parameters, whatever you feed into the model, and it outputs a single value, single point value for any given sort of multidimensional inputs. Now, of course, the problem is that when you compare the output of a deterministic model versus observations or real data, there is always a mismatch, and these mismatches are due to a number of uncertainties, epistemic, aleatoric, algorithmic, and so on. So the goal of this method is to take this deterministic model, take the real data, take all the information you have. Doesn't really distinguish between different sources of uncertainties, but what it does is to create, to generate what we call a heteroskedastic uncertainty, which is just a fancy word for saying it creates an error bar, which is a function of input. So it's not fixed, it changes as a function of input X, for instance. So this is a sort of a post hoc model that takes your deterministic model as a so-called oracle. Now, there are several ways of doing UQ, uncertainty quantification, in machine learning. This is a relatively new research topic. So just a sort of non-comprehensive list here. There are some parametric models, such as Bayesian neural networks, Monte Carlo dropout, ensemble techniques. All of these methods, unfortunately, suffer from the following: that the model output is typically not well calibrated or reliable. Now, I use depending what community you come from, you might use one or the other word. I use these words interchangeably, calibration and reliability. Then there are non-parametric models such as Gaussian process, which are, I believe, much more powerful. Unfortunately, these models do not scale very well with large data sets. Now, of course, there are also methods to do UQ with physics-based model, and typically the golden standard there is to estimate uncertainty running Monte Carlo ensemble, meaning that you have your physics-based simulation, for instance, and you slightly change your initial condition or boundary condition or whatever, and you run hundreds or thousands of ensemble members, and then you do a statistic on the output of interest. Now, this approach has mainly two problems. One is that it's fairly expensive, depending on how your physics-based model, how expensive that is. And so it requires many runs. But maybe most importantly, it requires to know what is the probability distribution of inputs and how to draw samples from that distribution. And quite often, those inputs are non-observable, so you don't even know what is the optimal distribution to take and how to draw samples from that distribution. So before going into the detail, let me just talk about give you the take-home message here. So this method, ACCRUE, is a method that estimates the uncertainties associated with single-point outputs generated by deterministic model in terms of Gaussian distributions. It does so by ensuring the optimal trade-off between accuracy and reliability. I will show in a minute what that means. The nice feature is that it does not need to run ensembles. So the computational cost is as much as training a neural network. So this is the paper which has been published this year. If you're interested in the details, and the code, a MATLAB code is available on Zenodo. Now, how does this work? It really follows sort of a utilitarian approach, if you wish. So just for the sake of a simple example, let's assume that for a single input X, which might be multidimensional, your model, your deterministic model predicts a given output y, and here I show graphically with the blue line the model output, and the red line is sort of your ground truth or your observed value. Now, the working hypothesis is that we want to use the model output as the mean of a Gaussian distribution, again, sort of an oracle in a machine learning jargon. And so the Gaussian distribution is interpreted as a probabilistic forecast. Now, if you do that, basically you're putting a Gaussian on top of this blue line. All that you have to estimate is sigma, or the width of this distribution. So the question you want to answer is, what is the optimal width of a Gaussian forecast? And the answer, I mean, the approach we are pushing here with ACCRUE is that the optimal width is the one that optimizes both accuracy and reliability. Now, what does that mean? So accuracy can be estimated or calculated in many different ways. We have chosen to use what is called the continuous rank probability score. This is a very well established metric in meteorology, especially, is a generalization of Breyer score. It is nice for many reasons. It has a simple graphical interpretation. Basically, if you take the CDF of your probabilistic prediction and the CDF associated with the single point output, the ground truth, the CRPS is related to the area between the two curves. So this is the formula, and it's a negatively oriented score, meaning that CRPS equals 0 means a perfect forecast. So this is good to use as a cost function. On the other hand, that's only one side of the coin. You also want to have a forecast which is reliable, and this is usually shown with a reliability diagram. So reliability is the property of a model that measures its statistical consistency with observations. So, for example, if you have discrete events, the reliability measures if an event occurs on average with frequency p when it has been predicted to occur with probability p. So if you show this on what's called a reliability diagram, where you have predicted probability on the horizontal axis and observed frequency on the vertical, you want to be on this diagonal blue line. If you're above, you're underconfident. If you're below, you are overconfident. Now, what is interesting and maybe is not so much appreciated is that, well, first of all, I mean, this is known, the values of sigma that minimizes the CRPS can be derived analytically. And I was saying what is not appreciated is that the more you minimize CRPS, meaning accuracy, the worse reliability you get. So the two features are really fighting one against each other. And this is just a toy, a made up example where you have different curves of reliability diagram. And if you go from the dark blue to the light blue, the CRPS decreases, meaning that your accuracy is getting better and better, but the reliability clearly gets worse. So this naturally gives rises to a true objective optimization problem, because again, reliability and accuracy are competing objects. So the way to solve this is to define accuracy reliability cost function, which is just the sum of the two with the scaling factor here. So once again, the two measures cannot both be minimized simultaneously. So we have to find the best trade-off. So how does the ACCRUE method works? So you take a sample of n errors sigma. So you have to have access again to your deterministic model, which works as an oracle, to the predictions and corresponding errors associated with those predictions. Again, we define as optimal standard deviation, the one that minimizes the accuracy reliability cost function. But we also want to have a way of generating, so again, the unknown here is sigma, the standard deviation. You want sigma as a function of x, whatever x is, and usually this is the input, those are the inputs of your deterministic model. And this is just a toy example in 1D actually, where x is the input, sigma x, the red line is the true value of sigma, which we sort of made up. And the model gives you this black, I mean, the black line here is the mean of several realizations of the model that you can see sort of captures the nonlinear behavior of sigma. So to do that, at the end of the day, this is a optimization problem that we solve with a neural network that takes x as the input and produces sigma of x as an output. So it's really general, it's model agnostic. It can be used on any deterministic model, whether it is a physics-based model, whether it is a machine learning model. Again, you just use that as your oracle. So we've tried that with several standard machine learning benchmark. Okay, this is a bit of a dense slide. You can see this in the paper. The bottom line here is that for all of those data sets, we compare different models, and the ACCRUE here is the one that most of the time outperforms the other model, both in minimizing the CRPS, so in the accuracy, and in the calibration error. So again, it gives you the best trade-off between calibration / reliability and accuracy. And this is again the take-home message I want to repeat, and the paper with all the details. And I'm ready to take any question, and thank you for your time.
Great talk, Enrico. Thank you for bringing that to this session here. Let me check Slack real quick. So as a reminder to our audience, please post your questions in Slack. That's where the conversation can live longer than our session. I don't see one there. In the spirit of time, I'll ask a question. I think maybe even just missed it. So in space science, we have a lot of phenomena that isn't, well, Gaussian distributed. Maybe it's log normally distributed, or maybe something more complicated. Can you speak a little bit more to the diversity of phenomena that this can or would need to be adjusted to take advantage of?
Yeah, as I said, the method is model agnostic, so it's not really tailored to a specific problem. What will happen if your residuals are not Gaussian is, of course, that the model gives you tries to fit the best Gaussian to your non-Gaussian residuals. But I guess the more appropriate way of doing it for non-Gaussian errors is to, you can always take any distribution and map that to a Gaussian distribution. So that would be sort of your pre-processing of your data to make it Gaussian, or at least as close as possible to a Gaussian. As you said, no, in space physics, for instance, many distributions are log normal, so you just work in the log space. And so that's sort of the main, I wouldn't say weakness, but the main constraint of the method is to work with Gaussians, and that's the reason why, if you look at the paper and the math, everything can be done analytically exactly for that reason, because we're working with Gaussians.
Okay, thank you. Yeah, that does help. That helps to appreciate. So mapping towards a Gaussian or normal distribution would kind of be an implicit or an explicit step you might take.
Which is, if I can add, which is, by the way, sort of the standard procedure in machine learning. When you train neural networks or whatnot, usually you always normalize your data typically to a Gaussian, because neural networks work better in the way. So it's not much different in that respect.
Thank you very much. I appreciate that. All right, so we will go to our last speaker, and if you have other questions for Enrico or the other speakers, please post those in Slack. I did see a question for Vidya that we might be able to get to at the end of our normal talks here. So without further ado, Matt, if you could go ahead and take over the screen and share your slides. So Matt is here to give us a talk on enhancements to VIAME, an open source do-it-yourself AI platform for environmental science, and this is a highlighted talk. Take it away, Matt.
All right, thanks, Rob. Just bring up my slides here. All right, so my name is Matt Dawkins, and I'm a software engineer at Kitware. You might remember me from last year's presentation, where we give a similar slide deck and tutorial at this conference for the first time. But I'm going to start today with a quick overview of VIAME, which is an open source toolkit that we're developing alongside fisheries, then follow up with some updates performed for the past few months for the second half of this presentation. So the first might be a repeat content for people who have seen some of our others, but the second should be new. So what is VIAME? Over time, it's evolved into a do-it-yourself toolkit that biologists can use to generate their own machine learning models with little or no programming experience, either in web or desktop interfaces. Additionally, we have recently added an online repository for storing related imagery and annotations corresponding to these imageries with some additional support for training models. Most of its current use so far has been on the first 3 items on the left of the below figure, particularly object detection and tracking. But more recently, we've been expanding its capabilities into stereo measurement, image enhancement, registration, low shot learning, 3D model generation, and a couple other fields. Lastly, it provides a few tools to assist with evaluating the performance of different algorithms, both while generating the models and after the fact. Both binary and source format, VIAME is released open source with a permissive license right on GitHub. A portion of its algorithms are highly specialized to particular domains and not present in some commercial offerings, but some are also very general purpose, so it can still be used on arbitrary image and video problems. People have begun applying VIAME to a range of challenging problems. For example, shown here are images from underwater or surface cameras. Some of these problems require the collection platforms to apply their own illumination and necessitates running image enhancement prior to automated detectors. Outward-facing cameras are a bit more diverse than some of the others, with a large range of different sensors targeting fish populations around the world. Tracking objects frame to frame typically becomes more important here to prevent duplicate counting the same organism, but it depends on the application. These might be underwater, onboard fishing vessels, or just cameras strapped to penguin heads. More recently, we've been seeing an increased amount of use amongst international organization partners, such as a few in the UK and the IFRAMER as well. Aerial surveys are also fairly popular, with most fisheries science centers around the US having pinniped detection programs from either manned fixed wings or small drones. So you can see here a diverse range of different climates with different types of seals and sea lions. Scene segmentation has also come up with a few groups, such as on the right, for classifying land cover into different categories, which is something we've historically not worked on too much in VIAME, though have been starting to this year. I'll talk a little bit more about it later. Lastly, we've seen people trying to detect other organisms from the air, such as the penguin colony showed on the bottom, but also things like whales and sharks over open water. This data might be from UAVs, fixed wings, or satellite. Planning for VIAME began in late 2015 with the formation of NOAA's Fisheries AISI Committee. The development picked up a bit more in 2016, 2017. VIAME was not the only product funded by ASI. Others include CoralNet, an open data store for containing coral annotations, and deep networks for classifying them. Additionally, some other algorithms as well, and specialized products. VIAME was originally designed to be an integration platform, though over time it evolved into a toolkit with a few workflows for generating and deploying models in a couple different interfaces. Due to multiple organizations having implementations of the same software components, one of the first things we worked on were sort of base classes for different versions of these. For example, color correction, object detection. New analytics can be added to the system via deriving these base classes in either C++, CUDA, Python, or MATLAB. Alternatively, new processes can be added independent of this class system by writing outputs into one of the few accepted file formats. While processes can be written in different languages, we lag behind a little bit in terms of Python support, but that's been increasing over time, especially because things like TensorFlow and PyTorch have led to a lot of developers doing deep learning development in there. Its backend, though, is still written in C++ to assist with speed and running on embedded platforms, even though you could derive some of those classes in Python. But more recently, we've been improving some of those APIs. Additionally, around 3 years ago, we started releasing binaries of the software so that end users didn't have to, say, build it from scratch. In terms of user workflows, which is really what it evolved into, the more traditional approach is sort of in the middle. The user has some raw data, they do a lot of manual annotations on them, then train up a model, and rinse and repeat until you're happy with the model. And by annotations, I usually mean, manually added or verified object labels or localizations around different objects of interest. Second is when you already have an existing model more similar to what you're trying to do, either from someone else's work or first pass model trained on the problem of interest. In these cases, it might be more helpful to correct the output of that existing model on new data, as opposed to performing annotations completely from scratch. That's generally problem dependent. The last workflow usually involves just training from a few samples in a completely different paradigm that I'll demo later, that uses a system of 3 convolutional neural nets for low shot learning. There are different types of annotations that the annotation interfaces and model trainers support: box level, pixel level, frame level, key points. Each are useful in slightly different circumstances depending on the application and user time available for annotation. Also, whether or not the problem calls for measurement or just detection. Additionally, there are a couple different interfaces, graphical interfaces in this case. The newest Dive is shown in this video, which can run either in the web or desktop. That was one of our main motivations for developing it. It supports multiple forms of annotations. They don't have to be exclusive. They can happen together on the same target. But more importantly, it supports sort of end-to-end workflows of loading in raw annotations, raw data, performing annotations on them, training up a model on multiple sequences, running that model on new data, and then lastly, exporting final analytics in a few forms. An open web portal of this client is available at viame.kitware.com with annotations that some users have made public. Then lastly, there's some more specialized desktop applications in addition to Dive, such as search for image search based on just a couple image examples of what you're looking for. Seal for multimodal joint annotation across different modalities, for example, thermal and optical, which is shown there. Besides graphical interfaces, project folders allow for bulk training and data processing without interfaces from BAT or shell scripts, which under the hood just use command line tools. But then there's multiple levels of configuration files and APIs for advanced users that offer a little bit more of customization for particular problems in terms of like the parameters you set. Lastly, there's an example folder in the desktop version that contains things that might not yet be in the interfaces that we're slowly working into there. For example, multi-camera pipelines is something that didn't exist in Dive that we added recently. So over the last few months, we've been making a few system level improvements, such as Windows installers with check marks for each feature, as opposed to one giant bulk .zip install. We've been adding GCP support via a few methods. So the first one there is you just host the entire web stack yourself on GCP or AWS, whatever your web client of choice is. The second one is where you take viame.kitware.com and you plug in basically your own GCP account so that you can export jobs onto more compute resources if you need them. So you want to have your own dedicated 4 GPUs. You can plug that into your account on viame.kitware.com. Also, you can import data that's hosted in the cloud. AI-assisted annotation is something we've been rolling out recently as too. That's basically pipelines to assist with, say, tracking or converting box to polygons. Polygons is something we've been working on more heavily this year. Traditionally, we've just worked in boxes because they're easier to make those annotations. You can do them faster. But we've been working on some AI assist tools to do a conversion. Typically, polygon models might offer 1 to 2% PD improvement, but again, that's completely problem-centric. Additionally, we've been working on expanding to new data types and sensors. For example, shown here are some satellite chlorophyll bands from a joint effort with Riverside Technologies that was presented earlier today. We hope to support other satellite formats later on in the year. Though not part of VIAME, that presentation also covered some text parsing and search, so looking for references and documents. Just to give you a very quick preview of VIAME's algorithms, I'm going to quickly go through a high-level slide of each component, show what's new and updated, but not linger on them too long. But if there's questions, feel free to answer after the fact. On the detection side, we've implemented a few algorithms from the wider computer vision community, such as FastRCNN, and there's also more specialized detectors created for individual problems. On top of some of these, we've added some features like automatic stopping criteria and learning rate stepping to try to ease the burden of parameter tuning on users who might not know much about CNN hyperparameters. Then additionally, VIAME has some other features, such as determining whether or not to grid a larger image into smaller tiles for improved small object detection, ensemble networks for fusing multiple detectors together, and fusing secondary information in, such as stereo or motion maps. Pixel classification I mentioned is something we're continuing to do some development on. We just integrated mask RCNN, but we're working on getting some user-facing networks for background classification into. Substrate classification and how to optimally fuse in auxiliary information like motion or depth maps is something we've been continuing on a joint effort with Kunemeset Farm Foundation, the later of which is also covered further in a poster on For For stereo measurement, as we speak, we're training an updated model based on some head-tail annotations we just received that were annotated in the Zoo Universe platform. They basically crowdsource these annotation out by Pacific Islands, but there's also 2 separate methods in the system for this. So in addition to just boxes and polygons, you might have head-tail for fish or other organisms. We've mostly been focused on fish just for the measurement problem so far. Similar to stereo measurement, we're updating our default fish tracker models based on an assembled data set with around 1 million annotations across 12 different groups, which contains about 1 million images. Besides that, though, VIAME has multiple tracking algorithms in it under the hood. For example, a registration-based tracker for low frame rate, high resolution aerial imagery, which might not be the same when you use on fish data. Well, you might want to use a more appearance-based tracking because it's generally higher frames per second video. You see a distribution of some of the data sets there. The 3 that are the largest components of this joint aggregate set are from Southeast Fisheries, California Department of Wildlife, and IFRMIR. But then there's a couple other smaller sets. Interactive search and rapid model generation. I'm not going to go into too much detail, but this basically allows you to do a query off of a limited number of samples. So it searches an archive for things that look similar to the image query of interest. And then there's a secondary stage called IQR, where the user can go in, mark off what was right, what was wrong out of the system returns to generate a model quickly. Showing a quick video of that. The user here has supplied a picture of a flounder. There's some preliminary returns. The user goes through, marks them off, what was right, what was wrong. While this is happening, the system under the hood is generating a model. Public VIAME, this process hasn't really changed much in the last year, though on some other government efforts, we've been making a web client version of this. So if people are interested in that, I would advise you to reach out. That bottom category here, things are, I know I'm explaining this really fast, but it's things that the classifier is more uncertain about. So the top would be the returns that are most similar to the query of interest. The bottom are things that are close to the decision boundary of the classifier. And the user here is performing multiple rounds of training where they annotate what was right, what was wrong. Between that, they train up a new model. In this case, it's sort of a rapid pass SVM. It's not a full deep learning model. But then some new returns are returned that the user can annotate. So for registration and mosaicing, we have a bit of ongoing work with Alaska Fisheries Marine Mammals Lab to process multi-camera system data and not duplicate counts for sea lions and pinnipeds. These camera systems might be all the same modality, or they might be some combination of optical, infrared, and ultraviolet, but they typically consist of multiple cameras side by side, each taking high resolution stills. As opposed to using planar homographies this year in our sort of high resolution tracker here, we've begun generating 3 maps, basically 3D stereo depth maps of the scene to account for elevation differences in some of these scenes to better, not duplicate count the same target. You have 2 baseline methods for full frame classification, which were recently added. Similar to some past examples, there's one method for where you have a lot of annotations and one for when you might only have a little, particularly a deep method and an SVM approach, respectively, trying to balance things out a little bit. The SVM is still sort of using deep learning because it just uses a CNN classifier trained in a supervised fashion, just lopping off the classification layers and using the feature vectors from the middle just with an SVM on top. So there's nothing super special happening in there. Lastly, many people are interested just in post-processing. They have hard drives big enough to record all their data and take it back to the lab and analyze. Though several also want to do image processing closer to the camera systems themselves. One such example was presented earlier today. My colleague Matt Brown covered a bit. It's also shown here just in case you missed that. But basically an open source system for drone deployment and deploying some of these algorithms on small quadcopters. So there are a number of next steps we're working on now, and additionally feature work. One near-term task, I touched on this a little bit, is updating some of these default models. Now that users have done a lot of annotations across different domains, deep learning annotations is critical. Many are also like a couple years old at this point. Other active areas of development include substrate classification, some of these background classification problems, some building up some of these AI assist annotation tools, exporting models to low shot frameworks such as TensorRT for embedded processing, and lastly, just supporting more data types within the system and expanding it to new fields. So, lastly, I just want to thank the people who have funded VIAME. I think we have a couple minutes for questions here if people have any.
Hi, Matt. Great. Thank you. Thank you for this wonderful talk. Yeah, I think quick time check. We do have a few minutes, and then we'll do the whole panel here. So let me look here. I think we've got a couple questions for you specifically. Nick asks, "Is Dive written in TypeScript?"
So the Dive interface is written in Vue.js, JavaScript, and Electron. The desktop application port is using Electron. The web version isn't. We also have something called GeoJS under the hood for a little bit of some of those things, but that's in contrast to our original interfaces, which were all C++, using Qt and VTK for visualization, so pure C++. But Dive is primarily JavaScript.
Okay, thank you. And these are from the Slack channel, so feel free to head over there and add. There's a second question. I also posed a couple, but we can save those for later. The next one is from Valentina, and they pose, can the history of the steps exported to reproduce, be exported to reproduce the experiments? Are these steps scriptable if one wishes to do that?
Yeah, I could answer that with a couple of mixed messages, but so you can do everything in scripts. You know, typically VIAME was made without graphical interfaces first, and then we wrap them, and these are sort of graphical interfaces. So there are pretty much scripts for doing pretty much everything. When we added like a new computer vision algorithm, typically we added to the binaries first without an interface component first, where it's just a script. In terms of reproducibility, that's a good question. And that depends on which framework you're using for detectors under the hood. So we're not actually using just one, we're using about 3. Our default training harness, which uses PyTorch, just with a couple custom training front ends, that does export a little bit of additional information alongside the trained weight file in a .zip file, including like a custom network architecture, but then a JSON file that has some information about what it was trained over, and learning rates and hyperparameter settings that the model was trained over. But not everything in the system does that or supports that, but some things do. You know, there's typically multiple things and factors you have to consider there, such as, you know, what was the exact training data used? What was the exact validation data you used? What was the exact model architecture you used? Hyperparameters for that architecture, software hashes as well. And some of those things are in there. But I think there's some tractability of performance we can still improve to those JSON files that are in there to have some additional information. Most of the interfaces on the desktop side, they don't really do history recording, but the Dive web interface, which is actually on the desktop side, that does record the history of the annotation changes you make. So you can undo them if you were to hose them for whatever reason. The prior C++ Qt interfaces didn't have that. But in terms of annotation, that might not be exactly what you're asking. Annotation history, you know, that is tracked every time there's a save action.
All right, thank you, Matt. That's good. Why don't we bring all our speakers kind of into a panel format here? And then there's a few other questions I see in the Slack we can kind of go through for the benefit of our audience. So I think if you stop sharing your screen, Matt, and I know we might have lost support from Lindsay, who was having some computer issues. All right, so let's see, do we have, okay, I can see Enrico, Matt, obviously, Vidya. And do we also have Mayank? Are you still with us? If you are, oh, great. All right. Okay, here's our panel. So let me just kind of tease through here. You can also ask each other questions. So I'm going to start with my question I started to write down. Watching VIAME and also the other talks, honestly, inspired me to ask this question about what are our thoughts on standardizing labeled data, especially when you have multiple frameworks, VIAME and others, that might be treating the same domain, trying to speciate fish in a certain area. What are our thoughts on trying to standardize on a taxonomy and an approach to storing labeled data? And I will, if anybody wants to go first, go for it. Otherwise, I'll pick on somebody.
So I think that I could jump in real quick, but it's great to have standards, and they definitely increase portability between different platforms. For example, if one company and another company, they want to take the training data from one, apply it to the other more easily, pull it down and have it work with a system, sort of off the shelf. They definitely make it easier. Obviously, it's incredibly difficult to get a room full of people to agree on something, and that'll always be the case. And you're never going to have one file format that does everything for everyone. That's just not going to work out. You're always going to have multiple different JSON schemas, maybe a CSV or two. But getting as close as possible to one core format that's supported across the board, and then you have a couple of offshoots from that. I think that makes a lot of sense where possible. Simply to increase portability between systems.
Right. It's a big topic for the for NOAA National Centers for Environmental Information, because we have our core data sets, and then it would be great when they get labeled to archive those alongside for further use. So thank you. That's good. I'll pick on another person. Vidya, would you like to share, since you show so much data labeling processes? You have some thoughts on that for your community?
Yes, that's a good question. I just want to talk about the image data that we developed recently in our project, and again, it depends on the area of interest. And typically, in our case, when you deal with the flooding data, you would see those 8 labels that we consider in your algorithm. Mostly, if you're dealing with like any type of floodings, in a small scale, that we found that those type of labels that, whether they impact our critical infrastructure, they, labels related to the forest or vegetation, and vehicles, those are common labels that we see in our data sets. That's, we need to, have a proper approach in order to detect them. And we found that our models that are doing a phenomenal job in detecting critical infrastructure, dams, bridges, but not doing good job with regards to forest or vegetation detection. So that's the point I want to mention about the image processing things. Thank you.
Oh yeah, thank you so much. Appreciate it. So if I missed somebody who would like to weigh in on this, please let me know before it. Otherwise, I'll try to kind of cherry pick something else in here. I waited the prescriptive 7 seconds there. We have actually one more question we didn't get to while you were giving your talk. Yeah, so let me find it. Okay, from Ethia, probably didn't pronounce your name right, I'm sorry. You posed, you use diverse data sets that are unstructured from various sources. What did you do to deal with feature selections and feature scaling? And so in other words, how are you able to combine these images with tabular data such as the river level data? Could you say a little more about that?
Yes, that's a great question. Actually, first of all, we focus on certain flooding events. We collected those data that occurred during a certain flooding event, during Hurricane Florence flooding, Hurricane Harvey, some flooding in Europe. And then, as I said, those images, we wanted to have geolocation information that we know where those floods occurred. And then once we get those data, then we started thinking that how we could possibly make them, format them and pre-process them in order to use in different methods. So what we've done that we use different pre-processing technique in order to make those images usable for various algorithms that we use in our modeling system. And the things that I want to mention here is, we get a lot of videos as well. In addition to, for instance, we have USGS river cameras, it gives us images. We have also, videos that our citizens, they share social media platform. And we develop an algorithm that in real time can capture the video and convert the video into time-lapse images, and then use it, pre-process it, and use it in the CNN model or any other deep learning algorithm. Yeah, I think that's the formatting of the data is very important. As if you deal with time series data, we format the data and then incorporate it in our modeling system. In here also the images, and then we want to make sure that they have the same dimensions, they have the same resolution and other related image characteristic in order to use them in the algorithm.
Thank you very much. So I want to also give a shout out to Mayank. Thank you so much for addressing some really interesting questions in the Slack. Did you want to add anything to the questions that were posed to you? There were several that you had a chance to address.
Sure, I think the questions are very interesting, and what I would recommend is, for anyone who is looking to apply this technology, I think the choice of the ontology is very important, and that is really where the domain expertise comes in. So once the ontology is there, then there are many open source tools. I didn't have a chance to go through them in today's talk, but if you search for information extraction or NLP, there's SPACY, there's the natural language toolkit. There are a number of open source tools that can be trained and be used to extract the information according to the ontology, and build your own knowledge graph that can be used in your systems. So I hope that the community will make use of these tools, because we're really in a golden period with the machine learning and the NLP, where there are so many easy to use tools, and especially if you combine it with domain expertise, So I hope people will try it out, and build knowledge graphs, and we'll come to hear about them in papers and other pieces of work that the community releases as they do this.
Thank you. All right, now final question, spirit of time, final question to Enrico. Well, thank you for addressing an initial question I had on non-normally distributed problems. I know you've seen kind of a broader diversity from space science to broader diversity of earth science talks here. You have a question kind of comes up again in a different spirit from Philip Tissot. Can the method be used adapted to non-normally distributed observations, which you said yes. I wonder if you would like to kind of add to that just a little bit more in the last couple of minutes in terms of how you see this model-independent methodology with accurate statistics, accurately representing observations being appropriate for across the earth sciences. You want to say something a little more about that?
Yeah. Again, thanks for the question. I mean, the way I see this method, as I said during my presentation, is that it really is model agnostic. Maybe something I could add is also the following. I think the method, and we've shown that in a paper as well, is also used. I mean, the first purpose of the method is to, as I said, to give you a probabilistic model out of a deterministic one. So I really sort of subscribe to the school of thought that a forecast is not really a forecast if it's not probabilistic, right? I mean, we are, again, and this might sound obvious to some of you. It really depends on where what field you come from. For instance, in space weather, which is my field, this is not really obvious. I mean, we only now are starting to do probabilistic forecast. But I want to say, so another way that this method can be applied to is to understand if your model, if your deterministic model has some systematic bias. In other words, once you plot your reliability diagram, and even after you do the probabilistic thing with ACCRUE, if your reliability diagram is not so good, one of the reasons may be that the overlying deterministic model has some bias. So this is a way of showing that up, because again, all that the method does is really to try to find the most optimal Gaussian distribution. And again, there is an assumption of Gaussianity which might not hold. So that might be one reason why your reliability diagram doesn't come out so well. But another one, especially if you've done this pre-processing into transforming your data into a normal distribution, might be that there is actually a bias in your model, like a systematic bias, like offset or something like that.
Thank you very much, Enrico. And actually, thank you all speakers, and thank you to our attendees who posed some really excellent and thought-provoking questions. Please continue the conversation in Slack, connect with each other, and hope you enjoy your next 15-minute break and attend the next session of your choice. Also want to thank Brian and Lindsay for helping this session run very smoothly. So thank you, everybody, and I hope you have a nice rest of your workshop.